Welcome, everyone. For those of you who do not know Codestar, we are a company of consultants who do functional reactive programming in the back end with Scala, in the front end with whatever tools we can get our hands on. And we work with streams of data, preferably, and do cool things with that. We have some cool projects. If you want to know anything about it, just ask one of our colleagues in the blue shirts. They will be able to tell you more than you want to know about it. Tonight we have a program, the first talk about data serialization from Maxim. Then we have a small break, some room for questions. And then the second talk, and after that some drinks. You're welcome to stay for drinks. Maxim is conference speaker as well. He's spoken at Berlin Bus, for instance. You've spoken a lot about data serialization and why you shouldn't use JSON, basically. You're also organizing your own conference about Swift, right? Yeah. iOS development. And you actually recently started with a new meetup group about ECS, the second topic for today. So if you're interested in that, you can go to Berlin up and down. Now, maybe it's also something for us, right? To have our own meetup on the topic, if you're all very interested in that, which I assume you will be. What's some other stuff that I want to show you? This one. This is our other events coming up soon. Surprise. We're going to organize some free Scala workshops for people who always wanted to get into Scala but never got the chance. And yeah, we're organizing on those dates. And if you go to the website or again speak to one of our people, we can see if we can still fit you in. Are we full already, Jan? Or are we full already with? Just say no. No, we have plenty of space. We have a wait list. But, good, that's the best answer. We have a wait list. Yeah, that's about it. I think we're ready to start. I think we have to get your mic on, but. Enjoy.
One, two, three, four, five, six, seven, 8. All right, thank you very much. Martin, thank you very much. Welcome. Thank you very much for coming. My name is Maxim, as already was mentioned. And the first talk will be about data serialization, and I would like to start with a short video. The video was kind of circulating on YouTube and Twitter, so you might have seen it, but it's actually like very good representation for one thing, how we do binary number representation, right? So this is a very nice physical one where you basically flip a number and then it goes here, and here you see the representation of this number, which goes from right to left. Really nice representation, right? Pretty cool. I was very happy that I could find this video so that it helps me to explain some simple topics. Okay. So the things that I would talk about is the nitty-gritty of data serialization. Okay. So in the beginning, we will start with just an underscore. What do I mean with underscore? It's basically 1 bit. With 1 bit, it's just we have only like 2 data points which we can represent, and it's normally like either true or false. Simple. Right? Then we go, yeah. So what is this supposed to be? I'll help you. My clicker, yeah. So for example, whole bit, whole byte, right? So it was from bit to byte. If we have 8 bits, we call it a byte. And with this one, we already can represent up to 256 data points. What do I mean by data points? Well, it depends, right? Sometimes we say we would like to just represent numbers, so numbers from 0 to 255, which we call also unsigned numbers. Then we also have signed numbers. Sometimes we would like to have like negative numbers as well, right? So there we basically just shift a little bit. So it's from minus 128 to this number. And then we also already can represent a character. So we can say like one character in ASCII or in UTF-8 can be represented in 1 byte. Okay. Now we have 2 bytes, right? Or I would like to represent it in shorter, so it's kind of like if I have this 3 underlines, then I say, because we can have in decimal numbers up to 255, I would like to represent it with 3 underscores. And like the pros are actually always represent bytes in hexadecimal, where you say from 0 to 9, and then A, B, C, D, E, F, which is nice because then you always have 2 characters to represent a byte. But to be honest with you, it's a little bit harder to imagine what is A7, for example. You really need to think. This is why I like to keep it in decimal, in a way, right? So 2 bytes, right? Who knows what little endian and big endian means? Few people. So I will explain still. So like the problem is if you have 2 things, then the question comes, should I read it from left to right or from right to left? And some architectures do it from right to left, some architectures do it from left to right. So people didn't really agree. People agree to read inside of the bits inside of the bytes from right to left, but how to order the bytes themselves, we have actually these 2 options, right? So as you can see here, if I would like to represent 5, I either represent it like this or like this. This is little endian, this is big endian. Good news is big endian's architectures are almost all of them gone. There are still a few, but the newest CPUs are actually little endian. So it kind of like, but still there are representations where you have to make a count for both of them. Okay, 2 bytes, we have about 75K of data points, and it means that we could have unsigned numbers, signed numbers, or characters in UTF-16. UTF-16 means basically that it needs 16 bits to represent a character. All right. Now we have 4 bytes, right? Lots of data points what we can represent, so about 4 billion, and then we say like, okay, unsigned numbers, signed numbers. Now we see here real numbers. We say 0 minus 0, which is 0, but still it's possible to represent it this way, not a number, infinity, negative infinity, and so-called single precision numbers. I will talk about them explicitly later, what it means. Then we have UTF-32, and then we have a pointer on architecture with 32 bits. 8 bytes, huge number, 1.8 with 19 zeros in a way, right? Again, unsigned numbers, signed numbers, double precision, real numbers, and pointer on architecture 64. Why do I list the pointers? So basically, if we use a language which has, and those are actually most of them, which have a concept of pointers, so referencing to another memory, then, for example, a data structure like a linked list. If we say we have linked lists of Booleans, a Boolean theoretically can be represented in 1 bit. Normally, we represent it in 1 byte. But as linked list is actually a reference into another memory point, on 32-bit architecture, we have actually 5 bytes for just storing 1 Boolean. And on the 64-bit architecture, we have 9 bytes, which we waste to represent only 1 node in a linked list. Okay? And actually, normally we have also memory alignment, so it will be not even 9 bytes, it will be 16 bytes for 1 true or false, which we will store. But I will talk in detail about this a little bit later. So, speaking of real numbers, how many real numbers are there, generally? Generally infinity, right? So the number of real numbers which we can have in math, so we can say like 0.00000, infinite amount of numbers, which we could represent. The problem is we don't have infinite amount of memory. And as we spoke about, we would like to represent it either in 4 bytes or in 8 bytes, right? So till this standard came along, it was kind of a wild, wild west. Every company kind of decided how they would like to solve this problem, representing infinite amount of data in a finite space, right? With EA754, now we have a standardized way how we would like to represent these things. So basically, what we have here 4 bytes, and then we say the left one represents if it's a positive number or negative. This is why in real numbers we can have 0 and -0. So if everything here is completely 0, it's 0. If it's 1, 0, 0, 0, 0, 0, 0, it's -0, which is actually the same thing, but we represent things in 2 ways, right? There is a special rule how to show infinity and not a number. And then there is a formula how you see the exponent and the fraction, how you manipulate with these numbers to have an approximation to the number that you would like to represent. If you are interested, there is a Wikipedia article on this, and you can read it there. So, double precision. Basically, 8 bytes, again, sign, the exponent is a little bit bigger, the fraction is a little bit bigger. So basically, this means that the approximation of the number is much closer. The interesting part is, for example, the number is 0.1, which is for us kind of a typical number. There is no way of representing it precisely. You will always have a little bit of like deviation from 0.1. This is why, for example, if you are comparing two float numbers or two doubles, most of the time it tells you that you should have a so-called epsilon. Epsilon is the smallest deviation that you can have, and you just subtract both these numbers, take the absolute value and see if it's actually the smallest deviation that you can have. Okay? Right. Last but not least, something which not used quite often, we also have so-called half precision, where we use just 2 bytes to represent real numbers. It's actually very imprecise, but for example, it's used in computer graphics a lot. Because in computer graphics, you basically have a loosey compression in a way. If something is a little bit off, it can be visible, but most of the time is actually good enough. But we have a very concise way of representing real numbers only in 2 bytes, okay? Which is half of 4 bytes and a fourth of 8 bytes, how we would represent it generally. Again, who works in kind of financial sector and so on and so forth? Who uses doubles for computation? You shouldn't. So basically, there are special data structures because you have these rounding errors. You shouldn't normally in a higher order languages like Java, C#, and so on and so forth. There are special types which are big decimal, which are actually more of data structures, which know how to represent it much more precisely. They are much more expensive to compute with and to store, but in this case, it's actually better to use them. Right. Okay, let's talk about string and text. With string and text, like we would like to represent like characters, right? And again, we just basically only have numbers. But we have those tables which tell us what number corresponds to what character, in a way. And this is ASCII. It's from it's a standard from '77 already, and this is actually like corresponds to the keyboard. So it depends on which key you press on your keyboard, it will generate one of these numbers. The numbers here are in hexadecimal. This is why you have the 00 prefix, and 30 is 3, 16, 48, I guess. Right, so for example, this one, 48, 49, 50, and so on and so forth. This is for the numbers. So this tells us how to translate. The problem is, this is ASCII, it's very old, and it's also only for Latin characters. What can we do if we, like, for example, have Russian or Chinese or even German have a few special characters? Like, what can we do there? So basically for these things, or nowadays, actually people can't communicate anymore without emoji. What do we do with emoji with this, right? There's no way. So we have a new standard, which is called Unicode. And Unicode defines the code itself, and then we have a few encoding methods how we can translate the codes into bytes, in a way, right? So with Unicode standard, what we have is, again, with 2 bytes, we can represent the basic multilingual plane, which is most of the typical languages, as far as I know. And then there are still other planes, which are up to 6 bytes, which kind of represent different other things. All right, so let's talk about UTF-8. With UTF-8, the idea is every character is just 1 byte, right? And the smart thing, what they did is, with ASCII, we have the typical characters which we have in an Latin alphabet. So all of this, they basically took over ASCII, which is only 7 bits, and told if we have a number which is representable in 7 bits, then it will be stored only in 1 byte. If it's a number which is bigger than 127, then we have a different encoding. We say here, the last bit is turning to 1, and then we know that we should also look at the next byte as well in order to decode the whole character. So basically here we see we have these 2 ones, meaning that we need to read 2 bytes in order to decode it. If it's even bigger number, then it's 3 ones, which means that we have to read 3 bytes in order to decode the character. And last but not least, 4 bytes for 4 ones at the left. So basically, this is a very smart way of saying we have kind of a compression, right? We can tell you how much you can read to decode the character itself. And it's stored in the most left bit that you're looking at. Okay, with UTF-16, we say, like, okay, we actually have 2 bytes. So if we have, this is the ASCII character, meaning we will still represent it with 2 bytes, not with 1, with 2. Now here is a character euro sign, right? It wasn't part of ASCII. It's quite new, right? But it still is representable in 2 bytes. Everything is fine. And then we have some characters which are larger, which have to be represented in 4 bytes, and it becomes 4 bytes. Here we can also see like those are the markers which tell us if we need to read next 2 bytes as well. Problem with UTF-16, like first of all, it was at some point a predominant encoding because people hoped that 2 bytes will be enough for everyone. So for example, Java, JavaScript, C#, and all the languages from the like late 90s to 2000 actually encode in UTF-16 per default. So if you have like Latin characters, you already like representing stuff in double amount of memory than you have to, in a way, right? And another problem is, as we said, it's 2 bytes already, right? The problem with 2 bytes, we need to understand, so do we read the left and then the right, or right and then the left? So we need the so-called BOM. This is the big endian order marker. So every text has to be prepended with a special number of 2 bytes, which tells you, okay, the numbers which come here are supposed to be read in little endian or in big endian. So again, a little bit wasteful, but still, if you think about it, you have a long string and then just 2 bytes in front. Not a biggie, but you shouldn't forget that you need to prepend it all the time because if we receive a file, we can't know if it was stored on the big endian machine or little endian machine. All right, human readable text-based serializations. Who knows CSV? Most of the people. Who knows Edifact? Really? Wow, okay. I didn't expect people to actually know that, that's cool. Who knows XML? Most of the people. JSON, yay, everyone knows JSON, everyone loves JSON currently. YAML? Who likes YAML? It's actually interesting, like in the beginning people actually loved it, until there was lots of configuration, lots of use of YAML, and then they started hating it. Because it's basically, when you start using it, you see like, okay, it's pretty, but if it's a big amount of data, yeah, okay. So TOML, few people, is just to simplify it. And Java property files, yay. So again, all of this stuff is basically for us a way to represent data, structured or in columns and so on and so forth, so that we can read it and write it, and then also the machine can parse it, in a way. The problem is, all of these text-based formats are second-level encoding, because we write it in text, and then this text will be either encoded in UTF-8 or UTF-16 or UTF-32. So basically, the numbers which end up depends on how we encode. Normally, UTF-8 is the one which always used. So I think there are very little usage of other formats when we store stuff. But still, if you think about it, it's a second level encoding, not the first one. So if we represent ints as text, we represent them in base 10. Means that, for example, if we have just from 0 to 9, this will be only 1 byte if we are using UTF-8 or ASCII, right? But if we say it's 255, we actually go into 3 bytes already. So meaning that if you have some form, if your data is very number heavy, you are kind of bloating it up, right? From the size up to 3, and you have to parse it, and you have parsing overhead. Because the numbers are representing characters. Then from this representation, you have to turn it into number representation, and then also apply like parse that actually to realize, okay, then you just have numbers themselves, and then you have to add them together until there is some kind of breakpoint where you see like this is actually one number. Make sense? Okay. Now, let's talk about real numbers as text. Minimum 3 bytes, because we say, okay, we're in UTF-8, and we would like to 0 point, 0 is character, point is a character, and then 1. Then 3 bytes, which is actually pretty cool, because otherwise we would waste 4 bytes. So here, yay for text, in a way, until we don't represent it in UTF-16 or UTF-32. Then we just explode it again a little bit, right? Then what you see is not what you get with an asterisk. So what do I mean with what you see is not what you get? If we, for example, write with 0.1, and the language which we use, programming language, will parse it into a double, it won't be 0.1 anymore, it will translate into some different number. And then we will maybe translate it into the text again, depends on the rounding implementations and so on and so forth, and we translate it again. So it could be that we actually diverge more and more and more from original number each time we translate it. With asterisks, it's basically because in some languages we have things like big decimal, which are complex data structures, which are defined to actually parse text and try to represent it as precise as possible. Again, they are configurable, so you could still say, like, I would like to round it like this, like that, I would like to store this precision or that precision, and you don't know if every language that you will use this data with actually has this kind of data structures which can interpret it, right? And again, parsing overhead. Right? Parsing real numbers is even more complex than parsing ints. Right, then sometimes we have to actually store bytes. Like for example, we have OAuth and we have this digest, which is just a stream of data in a way. And then if we use HTTP, normally, as far as I know, people just encoded base 16. So they look through bytes and encode it as numbers from 0 to 9 and use A until F for the representation. This means, however, that we lose about 2x of space again. So we bloating it up again, right? Base 64, you can, for example, use it in HTML if you would like to store images directly baked into HTML. There's a possibility to store them as text as well as base 64 representation, where we're losing 30%, which is like not that much, but still it's a little bit bigger. So you have an image of 2 megabytes, now you have an image of 2.6 megabytes. In a way. Okay. Forms of structured data representation. So basically, normally, how do we structure data? We structure it in tables, either row or column-based. Then we have trees, like for example, XML is the mother of all tree representations in a way, right? So it's kind of node, and then nodes, 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 and text, which is also node. So it's kind of like this kind of stuff. And then we have also graphs. Like, actually, I'm not familiar with any textual representation which can represent graphs. Like, if you're familiar with GraphViz, which is a graph representation, it has its like textual language how you can represent graphs as well. It's called dot notation. This is the closest that you, in my experience, what you can come to represent graphs with text in a way. You define nodes, and then you just basically say from this node, arrow to this node, and then you know how the connections are. In a way. I'm not talking about, so you always can represent graphs with other formats where you define an ID and just say like, okay, this is by ID, but it's a little bit a different thing. Because if you do referencing by IDs, you would have to have some kind of lookup table, which you will have to build up yourself in order to understand. You say like, my friend is 0.7, like number ID 55. So I would need to know who is 55, and this information is normally stored by the developer somewhere in a lookup table. Okay, so let's talk about binary serialization and what can we do in binary, right? Compared to text. We have a technique called bit pack. We have multiple bit packing techniques. What does bit packing means? It means that we will try to have as dense representation as possible. So we are not wasting space. We are trying to keep everything in the least amount of bits we can afford, in a way. It's not compression yet, because compression is mostly statistical. This one is just some smart ways of storing stuff in a concise way. Okay? For example, variable length quantity. What is it and why do we need to kind of, like, this one is very old. Who remembers Nitty, the format? Some people? So this was, Nitty was based on variable length quantity. What is the idea? As I showed you, like, we can, with numbers, we know that in 1 byte we only can represent 256 with 216K and so on and so forth. And beforehand, we actually don't know how large the numbers will be. So what we normally do also in runtime, we just say like, okay, just let's store this stuff in 8 bytes. If it's just 1 or trillion, whatever, it will all be represented only in 1 byte. With a variable length quantity, the idea is you only pay for what you need. Similar to UTF-8. The idea is that you have, now this is basically the representation of this number in big endian, because everything is in from right to left, right? And normally we would look it up in the chunks of 8, so it's bytes. But with VLQ, we say we will represent it in chunks of 7. And then we see that here, this will be just zeros, right? Because the number is represented here, this is just zeros. So we go through, here is the first chunk of 7, and we see, sorry, let's actually go from here. So basically, we take this chunk and see like there are still numbers over here. So we'll keep it here, and the last bit is 1, meaning that we have to go to the next byte. Here again, and here it's 0, so we know we are done. So basically, we are kind of losing 1 bit per chunk, but this is not a big waste in a way. Then there is also a thing called Zig Zag. Why do we need Zig Zag? Zig Zag is basically, the idea is if we have encoding and we say like 0 is here and 255 is here, then we say if it should be a signed number, then 0 is here and -1 is here. All the ones is -1. Which is problematic because what we normally do with bit packing, we're trying to get rid of zeros which are in 1 big chunk. So Zig Zag means that we say everything, if everything is 0, it's 0. If we have 0, 0, 0, 0, 1, it's -1. Then 0, 0, 0, 2, it's 1. So we go -1, 1, -2, 2, -3, 3, -4, 4. Okay? This is kind of the Zig Zag idea. So that we then, if we apply VLQ, then also small negative numbers will be represented small, and big negative numbers will be represented in lots of bytes. As we have a rule of big numbers, the number of big numbers is actually smaller, most of the time we work with smaller numbers, right? Who knows proto-buffers? This is a serialization format by Google, and this is the first thing that they explain to you if you actually look into the documentation of the format itself. Because this is the main idea how they make sure that the packages that you send are small. Okay? Then, another technique which we have for bit packing is basically we have even smaller numbers which we would like to pack in 1 byte. For example, array of booleans, right? Normally, booleans represented in 1 byte. If you have like a bool type in your language of your choice, it's actually 1 byte, but you could actually store it in 1 bit, meaning that you could store 8 values compared to only 1 value, right? So if you have an array of booleans, you can create a so-called bit array, which will be very compact, okay? Otherwise, we could have enums. Enums are normally also, sometimes there are lots of cases, but most of the time it's just maybe 2 cases, 4 cases, 16 cases. If you have 16 cases, you could actually pack together 2 properties in an object in only 1 byte, meaning bit packing, right? Squeezing the last smallest amount of memory kind of inside. Okay, deduplication. For example, this means that we have values which are actually big and they are quite repetitive. Example is GIF. With GIF, we have a so-called palette. So every pixel or every color is represented in 3 bytes. RGB 256 each, right? 3 bytes. So what does GIF do? GIF creates goes through the picture and just creates a palette of 256 colors which are used in this picture. If there are more, then they will be squished basically. So you will lose color. And then every pixel is represented only with 1 byte, with the position in the palette. Meaning that we have an overhead of the palette. So we have 256 multiplied by 3. This is like the palette size. But dependent on how big the image is, how many pixels we have to store, it's actually a win. You can just basically try to define a form and see when it becomes actually a winning situation and not losing, right? And then again, if you have GIF, you have animation, so you have multiple images, which will be stored in much precise way, okay? Then another technique which you can apply is say like, okay, I'm actually storing in this palette, I only store the frequent stuff, and then I have a marker saying like if, for example, 0, so from 1 to 255, look up in the palette. If it's 0, then it's stored in place, in a way. In this case, you kind of have the rule of the big numbers. There will be much more data points which can be in the palette, and some of them are falling out, but you're not losing them. They are still stored there. Okay? Then what you also can do is store deltas. Specifically, if you have a sequence of numbers, and you have big numbers, so I don't know, if you would like to have double precision, but you know that the change is quite small. So this you could represent, for example, in half precision. You have steps. Therefore, you can just store like the initial number in big, and then just small changes which work this way. For example, the video codecs like MPEG, they work the same, similar way. You have the initial frame, and then they store just the pixels which change until they have, again, one full frame, and then just changes. So for example, if you have some kind of problem with buffering, or you jump somewhere, you can see that the picture in the beginning is kind of weird because you just seen the deltas, and then at some point you will see the whole picture and then just deltas. Okay. Memory alignment. So what I spoke about before was how can we pack this stuff as dense as possible, okay? But sometimes we would like to actually be able to pack it, like do something like what Amazon delivery system does. Put everything in the big boxes, just because then we know how to solve the knapsack problem. Who knows the knapsack problem? Some people, it's basically the idea is kind of you have knapsack, you have, and you have different items, and you would like to put as many items inside. And sometimes if you put something too big, then you would be able to put only a few small things, and you would like to optimize this. So the idea here is basically I would like to store things like I store them in memory, for example, arrays. I know I have an array of 4-byte numbers. The good thing about this, I know if I would like to, I have this, I don't know, 1 million numbers, and I would like to read the number 250. If I have bit packing, I wouldn't know where to jump to, because they are all in different sizes. You would have to iterate through them to actually find the one which is 256. However, if they are all aligned, 4 bytes for everyone, then I know 256 is at position 256 multiplied by 4. I can just directly jump to it and then just read values starting from 256. For this, I need alignment. The problem is, for example, we never have it with textual representation because there we really need to first decode everything to have this kind of aligned representations. With binary, we can choose to say, we will waste memory, but we have this possibility for random access into things. Okay? So, binary encoding formats. Who knows protobuf? I already asked only a couple of people, right? This is basically a format designed by Google. It's actually quite old. As far as I know, they started working on this 2001, and they used it internally for service-to-service communication because they needed something very efficient. And the representation is, it uses VLQ, it has lots of smart things how you can do stuff. So as well, it also has a schema, and it has a code generation step, meaning that you have this schema, this textual representation, how a message can look like. Then you have a code generator, which will generate code in different languages. And as a programmer, you actually use already a very nice API in order to build these messages very efficiently and then serialize them and send them somewhere. Okay? They do use big packing, VLQ, for example, and then the data can be hierarchical. So basically, some kind of similar, a little bit similar to JSON in a way, right? So you have objects with properties, you can have enums, you can have so-called unions. Union is something where you say like, it's like a protocol. So you say like, it is, for example, it's a shape, it can be a rectangle, circle, triangle, so that I know what kind of type it is, and I will have to check which representation is it in detail. Anyway, okay, then there is BSON. Who knows BSON? Much more people? Actually, to be honest with you, I'm not that familiar with this format. I know that its representation is basically the MongoDB answer for JSON in a way, saying like, okay, we do it in binary. The problem is everything that I looked about it, like it's actually quite big comparing to, for example, protobuf or message pack. So it's not that efficient in the storing. I'm not sure if it's really efficient in reading. I think as well, not really. It's also, so again, I'm not really an expert on this one, but it's something, if you are interested, you can look it up. Message pack is as well an answer for JSON, but it's actually does some bit packing, so it tries to have a very small representation, and it do it in a way that it stores the type. So for example, if you store a number, it will prepend it with information if it's now 1 byte, 2 byte, 4 byte, or 8 byte representation. Therefore, you're losing 1 byte for every number in a way, but you are winning compared to storing this stuff just always with 8 bytes. Okay, then SBE, who knows this one? It's simple binary something something. Nobody knows it. It's from, so basically this one's supposed to be very efficient. It's schema-based, also have code generation, bit packing, and you can represent hierarchies. And again, interesting point, evolutions. What do I mean by this? So like the idea is following. If you have an evolution strategy, this means that you have a schema. And as always, if you define something once, you would like to change it at some point, right? So with evolution strategies, you have certain rule how you can evolve this schema so that if you have a new version or you would like to change something, new code could still read old data, which was serialized by old code. And then also, old code can read new data. One is called backwards compatibility. The other is called forwards compatibility. This is very important, so people normally don't care about it until it's too late. Right? So it's normally saying like, okay, like we will just make it work, and then at some point you have to change it, and if you don't have an evolution strategy, then you have huge problems. So you either have to version stuff and see that it doesn't break for you and so on and so forth. If you have evolution strategies already in there, then it's actually very beneficial. Right. Then flat buffers is another format designed at Google, but it's more recent and it comes from a different area. It comes from the game initiative that they have. So they had an initiative to help game developers come to Android platform. For this, they developed a few libraries and so on and so forth so that people adopt Android and start developing games for Android. And flat buffers is a child of this initiative in a way. Right, so here you have a schema, you have code generation step. This one is random access, meaning that it's actually memory aligned. If you already loaded the whole data, you don't have to parse it or interpret it in any other ways. The generated code can directly read the values out of it. So you don't have to copy, like you loaded data into memory, you don't have to copy it again in a way which your CPU can deal with. You can directly access values directly in this data. Flex buffers is actually like a sub-project from flat buffers, and this one also is random access, but without the code generation. So there is no schema. It's actually kind of as well an answer to JSON, saying that we can store stuff self-represented, but we have a possibility of random access. We don't have to parse. We don't have to unmarshal in any kind. And then we have, again, Captain Proto, Seaboard. Who knows Parquet? Parquet? People who do probably data science stuff and so on and so forth, so big data, right? This one is interesting because it's a tabular representation, and it's column first. So basically, why is column column-oriented representation is better? It is better because then you have similar representation of data, which you can align directly in the same way, right? This way you can jump to things, to say like, I would like to not read the whole 10 terabytes of funny cat pictures. I would like to just jump to this portion and just read this portion. This is what you can do, for example, with Parquet. Parquet is, however, trimmed as a format for storing on file. And it has regions with headers which tell you how this stuff is also compressed. There is another one which was born after Parquet as a solution for in-memory storing. So this one is basically designed as well column-based, but more to store stuff in memory and just directly read it from memory. And then it's as well Apache Avro, and so on and so forth. Right. If you are interested in Parquet and Arrow, there is a good talk to it on YouTube. So if you evaluate binary serialization formats, there are 4 points, I think, which are important. The format specification itself, the code, which is used to serialize and deserialize it, or read and write it in a way, then the schema and the tooling for human readable. All right. So format specification, it depends on your use case, right? So support for endianness and architectures. It could be that you don't care, you're always on little endian because you always work on the newest architectures and so on and so forth, so you don't care. But if you, for example, need to do like low-level stuff or, I don't know, IoT embedded, then it could be important to see if this format is actually supporting different architectures and different endianness, right? Then it depends on you if you need bit packing or memory alignment. So basically, would you like things to be small? Because, for example, you need to send them over the network, and this is your main bottleneck? Or it's something which will be read a lot of time. So, for example, you have this big amount of data, and you would like to be able to read it very efficiently without generating lots of temporary memory, where we come to the point 3, need for temporary memory allocation. Again, from the format, you can already kind of think about, like, is it for this format needed to unpack this? If you have bit packing, probably at least for unpacking the bits, it will cost you a little bit of temporary memory to be able to unpack it and then just throw it away. Okay. And then the form of data representation, we'll talk more about it in the schema. And then, again, I think it's very important evolution strategies. Specifically, if you in a bad situation to work on something successful, which needs multiple versions and be evolved, then it will help you a lot if there are already evolution strategies baked into the format. Okay, code. First of all, is the code generated or is it a library? Sometimes it's both. Actually, the generated code uses library. So it depends on your situation. If sometimes people say, like, I don't want to have any code generation at all because I don't like it, I don't trust it, whatever, or my build pipeline becomes really complicated because of it. Therefore, you can see if code generation is there or not. Then, for sure, supported languages, if your languages are supported, which you use. Then, computational efficiency. A format can be very efficient, But if the library is not efficient, the code which actually does the work is not efficient, then who cares? And it's actually, as well, very important. There are always lots of ways how you can optimize stuff. So basically, it's important to have a little bit of a benchmark to see if it actually like applies to your expectations that you have. Okay? And then we have memory versus speed. So basically, the whole thing with would I like to have like random access, or would I like to have the smallest amount of memory consumed? I don't know. Clicker sometimes works, sometimes doesn't. Then, are we schema-based or self-describing, right? Sometimes it's important. Like, I talked with some people and I agree with their point. They say, like, if you have something schemaless, you are just delaying the problem. Because in a way, with schema, some people say, like, okay, I have to think up front. I have to actually design, think about how this data is represented. If I have something like schemaless, like JSON, then I just write. The problem is at some point, you will have to think about it anyways. And at this point, it's always much, much, much harder to think about it because you already have something, and it's already working, and it's critical, and it gets to lots of pain, in a way. Right. Then language and tooling. So if you have a schema, what is the tooling for this? Is it just text and you have some command line tool which generates stuff, or is there something more? Then you need to think about high-level concepts. So what do you actually need, right? So is it okay for you to have something just tabular? Would you like to have something more like JSON where you can divide hierarchies? You say, I have this kind of object which has properties, and then I would like to have an array. I would like to have unions, for example, as I explained before, where it's a type, but it can be a different type of types, anyway. Right? And then this one is also important, specifically if you're working with multiple people. For example, JSON doesn't have a possibility to create a comments, in a way, right? And it would be nice if you have a schema where you can put comment to describe what it actually is. Your properties should be self-describing, but still, it's sometimes important to have documentation inside. And some of the formats actually support that the comments that you have in schema will be translated to the generated code as well. So the classes which are generated are annotated with the same comments that you had in your schema as well. Okay, then tooling for human readable. So like the main point why we use human readable formats, text formats like JSON, XML, so on and so forth. It is basically because they are human readable, right? And it's important for us because we develop this stuff. It's really hard if something is not readable, then you just don't know what it is. But most of the time there is tooling to take the binary representation and turn it in a textual representation. Or if you are very lucky, or you can build it yourself, you can also build a GUI for this, right? To say like, okay, because most of the time, as you already generating code which can read this stuff, then it's quite easy to put UI on top to say like, okay, I would be able to just represent it in a visual way somewhere. Then if you're very lucky, then you also have an import of, for example, directly from your database into this format, right? For example, Parquet and so on and so forth, as far as I know, there are multiple possibilities to integrate. Okay, so benefits of binary formats. Compact size. Most of the time, it's much more concise than textual representation. The only thing where it could be a little bit interesting is if you have CSV, and then most of your data is text. Then it's probably you will be kind of on par, and so on and so forth. If you have lots of numeric data, then binary serialization should be better. and higher. Then efficiency in read and write. As I told you, textual representation is second level encoding with parsing step involved. So it can be a tremendously good parser, but it's still, you need to parse. This is still a step which it doesn't go away. It's still there, even though someone implemented the best XML or JSON parser or CSV parser, still there will be an overhead, which you can mitigate if you using a binary serialization format. And then the problem of human readable, it's about tooling in the first place, because the text, as it's stored on disk, the UTF-8 encoding, we can't read it either, but we have a text editor, which transforms these numbers into text for us. If we have tooling which does the same with a binary representation, then it's basically the same for us. Or even could be better, depends on the tooling you have. Okay, and then basically with this overhead, if we think about it, I heard about that the data centers consume about 4% of worldwide electricity currently. How much is actually spent on serializing, deserializing textual representations? My guess is quite a bit. Because basically, if you think about it, like most of the stuff that we send to each other is mostly in textual representation. If we get rid of this overhead, we might get a smaller number in the long run. Okay, thank you. Yeah. How am I in time, actually?
Thank you. Yes, thank you. So, does anyone have a question? Yeah, one.
But play devil's advocate. What is wrong with JSON?
True. So, like, the problem is it has to be parsed, right? So, first of all. Then it's self-describing. Meaning that, for example, if you have an array of objects which are equal, you are repeating the keys over and over and over and over and over again, right? Meaning that you are basically wasting not only the CPU power for parsing this, but also the amount of data that you're sending is normally 3 to 4 times as big. Because if you compare, for example, to protobuf or other representations which has the same, so you are basically representing the same data just in a very, let's call it naive way, which you could do better in a way. And this is why I think like it is something which had to be like thought about. Because again, for example, data centers, they just receive JSON all the time. You have an endpoint. What does your endpoint do? First of all, parse JSON to actually just to understand like, okay, do I need it or not? Yeah.
Have you heard of VelociPack? VelociPack?
VelociPack, not yet, no.
Yeah, I only know it from ArangoDB, where it's used as its internal storing format.
Okay. Do you know, is it basically the idea is to have the smallest amount, or is it
small and then quick access?
Okay, okay.
Yeah.
I'll have a look. Thank you.
So apparently all these different ways of encoding data have different density and different computation needs to get the data back out. Are there any generally accepted metrics to express the efficiency of these protocols?
To be honest with you, I'm not aware of them. There are sometimes, there is, for example, repository on GitHub which have all the Java serialization. So they have like 60 different Java formats which they compare with each other. And then the problem is you can see there, but first of all, it's a micro benchmark. So it always depends a little bit on what kind of use case you choose. And sometimes the implementations are also inefficient. So for example, I'm very proficient in flat buffers because I ported it to Swift, for example. And I saw the implementation there. They actually didn't use the direct value access. They mapped it into POJOs, which basically just like ruined all the why you should use flat buffers in the first place. You should use it so that you can avoid the replication of data and avoid the stack allocations, heap allocations, and so on and so forth, right? And it always a little bit depends on. It would be nice to have a platform which does it in a way professionally, so that you can just go there and there you can try out also with your own use cases. But sadly, I haven't seen this kind of stuff yet.
Okay, thank you.
Any other questions? Yes.
So on your own projects, is there one specific format that you use all the time, or do you use different ones on multiple occasions?
It depends a little bit. Like I have a soft spot for flat buffers because I also kind of ported it and I know it the best for all the internals and so on and so forth. But again, this one is interesting if you need random access, but if you need something really concise, I guess I would go with protobuf if you would like to have a schema and then proper evolution strategies. If you don't want to have a schema, you could try with message pack, I think. And it really depends a little bit on the situation, what kind of data you have as well. So for example, if you can have a tabular structure, then I would also have a look into Avro and maybe even Parquet and so on and so forth.
And if you have files on your file system, can you recognize them? What way they're encoded?
You should know. So basically, like the point is, for example, some of them have specific tags in the beginning, so that you can see what it is. So for example, in flat buffers, it's not necessary, but you can define name of a file in a way. And if you see this on the fourth, it's like 4 bytes on the 4th byte. If you will see it there, you know, okay, it's flat buffers. With smaller formats which do bit packing, probably not, but they are also normally used rather for communication. You have basically, with data serialization, you have kind of two big fields of use. It's either it's communication, right, between services or whatever, or it's about storing stuff. If you're storing stuff, I guess as well Parquet should have something. I'm not 100% sure because it's actually trimmed for, it's specialized into having big files for big data. So I would expect that they have some kind of tags in the beginning so you can see that, this is a Parquet file. But
there's not something like a file extension or anything.
File extension you can add, right? But it's up to you then.
No, it's not a standard thing.
Yeah, it's not a standard
like
thing.
JSON has JSON and
yeah,
XML has XML.
Yeah, sure. So, like as far as I know, I haven't seen special file extensions for special formats. I guess primarily because lots of the formats are actually used for communication, and not that many of them for storing.
Yeah, one thing I was wondering about is like human readable optimized formats are also easier to search sometimes. Because if you like want to find something in a string and you just know it has to be this name, if your whole file is encoded in a way, then that can be harder, I guess.
Again, depends on the tooling, right? So it's easier for you to search. I guess you open it up in a text editor and then you search for this pattern, right? And then basically what the text editor does is just streams through the whole file and find this pattern for you. You can do the same with binary, actually. It doesn't matter. You just need, there are already binary, like general purpose binary visualization tools, which just shows you binary. If you can search for patterns in there, to be honest with you, I don't know. I didn't try, but I don't know why not. Because
the only problem is if I then don't find anything, I'm not sure if I made a mistake in my code for searching or that it's not there.
Again, if it's, for example, a string, then I would expect it to have human-readable string which you type in, and then it tries to find it in human-readable way. As well, those general purpose binary, not editors, but viewers, basically, if they see that the number corresponds to ASCII, they per default show you the characters, actually. This is what they do per default anyway. So you will, actually, if you open it with this kind of viewer, you actually just see like garbage, 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 text, Maxim, for example, okay. And then garbage, 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 Zaks, okay. Kind of something like this, right? So it's actually, it's not as bad as you would hope, right? Or think. Hope is probably the wrong word, sorry. Yeah, but again, it's a question of tooling because, like, for example, again, in this presentation, I didn't show it, but I have another presentation where I have an API called to Giphy.com, where I just want to have 25 GIFs. I just need 25 URLs, right? They return 25 kilobytes of JSON, having all kind of stuff. When you have 25,000 characters formatted as JSON without pretty printing, this is not human readable anymore as well. You can still search in it, but it's, again, it's just a wall of characters for you as well, right? And it's, there I actually make my case if you would like to pretty print JSON, then it again becomes like 1.6x of the size of minified JSON. And the interesting part as well, like for example, as an endpoint, I can't guarantee that the JSON I receive is not pretty printed. Because I don't know that. I would have to, I could open a JSON object, write two properties, and then fill it with 2 megabytes of space and close it. This is a valid JSON. Your parser should parse it. It will take forever to actually scan through all this, like forever, to scan through all this white spaces, but theoretically, this is an angle for DOS attack, right? So it is still valid JSON, it's still valid payload. You would, on your side, you would have to just say, I accept only payloads of certain size. Then if I see, because I'm sure it should be possible to send me all this data in 20 kilobytes, for example, right? If it's not, then I'll just reject it by default. But if you don't have this kind of stuff and you would like to just feed it to your parser, then it will actually do work which is completely unnecessary, trying to find the end of the object, for example.
Yeah, thank you.
Okay.
I think
There is a last question, I think, or
in the break.
in the break. Okay, cool.
We're going to go to the break in a moment. First thing I want to say is we have an arcade in the back, so you're welcome to use it. The one with the highest score for tonight, we have a small prize. And we have a 15-minute break. You can still grab some drinks, and I'll see you in 50 minutes, 8 o'clock.